the idea of a probabilistic center of mass, expectation, and a probabilistic moment of inertia, variance, carries over smoothly from the discrete domain to the continuous domain. Naturally enough, all that the student will have to keep in mind is that the chance variables have gone from discrete to continuous, and so probability masses give way naturally to probability mass densities, and sums segue naturally into integrals. And if she keeps these basic ideas in mind, then she will find the arguments carry through without essential change. So, without further ado, let's begin by considering a continuous sample space. The sample space here is a real line. We have a continuum of possibilities. Recall that in such settings we call sample points, these idealized outcomes of an experiment, random variables, an evocative terminology which suggests that we have a chance experiment which is going to spit out a real number, and that real number naturally we'll call a random variable. Again, traditionally, we'll denote a generic such random variable by an uppercase letter x. So this represents a chance-driven real number. The question, of course, is, well, what is the probability measure underlying this experiment? And in the continuum, this is given to us by the specification of a density function. Recall that a probability density function P of x represents a probability mass per unit length at a point x. Since it represents a mass, it must satisfy the basic axiomatic principles we began with for probability measure. In particular, P of x has to be a non-negative function, and it has got to be properly normalized. The area under the curve must be unit. Now, with this to begin, consider the weighted sum, let's call this mu, of taking a real number x, weighting it according to the mass that your random variable uppercase x places near little x, and simply summing, or, of course, now in the continuum, the sum segues into an integral over all possibilities for x. What have we done here? We formed a weighted integral of possible values of a chance experiment. And we've had a name for this. Of course, this is exactly what we called the expectation of x. Of course, here's an expression for the expectation of x in the continuum. A beginning student should feel free to argue by analogy. Remember, in discrete settings, we had probability mass functions which put probability mass at individual points. Averaging out the values that the variable takes in accordance to the mass function gave us an expectation. When one moves to the continuum, mass functions give way naturally to mass densities, which have units of mass per unit length. You have a continuum of possibilities. And sums now segue naturally into integrals. An integral is nothing but a limiting stylized sum. And therefore we have it, completely in analogy with what we've done in discrete settings for the binomial and the Poisson variables. Here now is an expression for the expectation of a continuous random variable. This stands for a probabilistic center of mass. Now, before I move on, there is a small caveat that we have to put in place. The integral we have here is formally an improper Riemann integral. Its limits are at minus infinity and plus infinity. And if a student thinks back to her calculus class, she might recall that there is an inconvenient possibility that integrals of this form do not converge. All right, so we have to take cognizance of such a possibility. We say that this expression mu is the expectation of x, also written e of x, provided that integral is absolutely convergent. Okay, Now, with that caveat in mind, let us think about ideas of spread. As always, let's call sigma squared the integrated squared deviations of x from its center mu. X minus mu tells you the distance of x from mu, positive or negative. Squaring it gives us a squared distance of x from mu, weighted in accordance to the mass near the point x, p of x dx, and integrate over all possibilities for x, and you've got an expected squared deviation from the center. Of course, this is what we call the variance of a random variable. Recall that variance just connotes a probabilistic moment of inertia. And now there you have it. Completely by analogy in the discrete setting, sums segue naturally to integrals, and otherwise nothing much changes, with just a little caveat in the back of our minds that these things actually have to converge for us to say something sensible about them. And so now we have these ideas of a probabilistic center of mass and a probabilistic moment of inertia. We call them the expectation and the variance. Now, before we move on, let us look at a small variation on this theme. Okay. When we start with an experiment, we have a coordinate random variable, say uppercase x. Now, it is frequently the case that we start with such a chance observation and then we process it. We pass this chance observation through a transformation, a function. And in this way, we obtain new chance variables. So let's consider again the setting where we have a coordinate random variable, uppercase x, which is equipped with a probability law, a density p of x. Now suppose we consider a transformation where we take x, pass it through a given function f, and spit out a value y. Of course, you are very familiar with such a notation from your elementary calculus classes. What is f? Well, at this time being, I'm going to keep it very, very general and abstract. F could be any generic reasonable function that you could think of. For example, you could think of y as x squared. It's a quadratic function. Or y is e to the power x, an exponential function. Generically, any reasonable function. Here's a transformation at hand. Suppose we look at this transformed variable and form the following weighted sum, or more precisely, a weighted integral. As x ranges over all possibilities, look at the value of the function f of x at the point x. Weight it in accordance with a mass that your coordinate random variable places near x, px dx. Sum over all possibilities, integrate over all possibilities, and Bob's your uncle. There you got a value m, again with a proviso, the caveat, provided that integral converges. Right? If the integral converges, then we have nothing to say on the matter. Now, what does it remind you of? Of course, it reminds you of an expectation. What is it an expectation of? As x ranges over all possibilities, you're looking at the expected value, the center of mass, for f of x. Naturally, we'll call this the expectation of f of x. This is now standing in place of our usual formulation for expectation for y. In fact, this is exactly the expectation for y. Of course, you will observe that if you want to try to write an expectation for y, then our expression involved an integral over y values weighted according to the mass density for y. All we have done to obtain this alternative expression is do what is very familiar. We have run this integral through a change of variable, replaced y by f of x, and there you have it. You have an alternate expression for the expectation of y. This turns out to be very useful because this tells us that in order to find the probabilistic central mass of y, the expectation of y, it is not necessary to first figure out what the probability measure of y is. That is induced via a potentially complicated process through p of x and f. Now, to find the center of mass, it will suffice to simply integrate over all x possibilities, weighting the values f of x. Of course, we can promptly do something very similar with the variance. Right? Let's call S squared the weighted integral where we look at the values f of x at a given point x, ask how far is it from the center M, square it. Now we've got the square distance from the center, weight it in accordance with the mass density near x, integrate over all possibilities, and what do you have? Naturally, the variance, the probabilistic moment of inertia of f of x. In other words, we've got another expression for the variance of y. Now, this is going to be useful for us shortly, but let me take it one step further because we have some low-hanging fruit here, and this is going to be easy to grasp. What if we have a coordinate transformation in more than one dimension, in 2 or more dimensions? This is now going to lead us into a function of 2 or more variables. And I should warn you that notation is going to ineluctably get more complex. We have now many balls in the air because there are going to be many trials, and we're going to have to keep track of which ball is which trial is which. Notation is going to get more complex. But with that as a proviso, the essential logic of the situation is not going to change. And if you keep your eye firmly on the logic of the situation, then all these expressions will become completely transparent. So, to begin, suppose we have an experiment which comprises a system of n probabilistic trials. The outcomes of these trials, let's call naturally x1, x2, x3 through xn. x1 through xn represent random variables, each from its own chance experiment. The composite experiment gives us an idealized outcome, a sample point, which is now a random vector, an n-tuple of individual possibilities. This random vector lives in a Euclidean n-dimensional space. If you feel more comfortable with something concrete, think of n as 2, and we're dealing with a Euclidean plane. If n is 3, we're dealing with ordinary 3-dimensional space. And more generally, for higher values of n, we'll deal with it algebraically in terms of an ordered n-tuple. Of course, this is a chance-driven experiment. Each individual trial results in an a priori unpredictable outcome. So the composite outcome is going to be unpredictable. It's governed by a probability law. We are dealing in a continuous space. The law then is going to be governed by a mass density. Now, as a function of n variables, p of x1 through xn. What does this connote? It connotes the probabilistic mass per unit n-dimensional volume at the point x1 through xn. Of course, you'll recall that a probability density of this nature has to be positive and has to integrate to 1. These are the positivity and normalization axioms. Now, with this to start, consider a transformation. Think of these as coordinate variables or observed variables. A transformation massages these variables and gives rise to a new variable, y, which is a function of x1 through xn. Think of your favorite function of n variables and imagine that is your f. Y, of course, now is a new chance variable. It inherits its chance law, its probability measure, from the underlying measure from x1 through xn, which is governed by the density p of x1 through xn. Right? Suppose we were interested in the expectation and the variance of y. We'll do exactly what we did in one dimension. Look at a point in n dimensions, x1 through xn. The function value, the y value at that point is f of x1 through xn. Weight it according to the mass that your random vector places at and near that region. Integrate over all possibilities by allowing x1 through xn to vary over a whole space. The result gives you a value m with the proviso, assuming that these integrals converge. And of course, this is naturally what we'll call the expectation of f of x1 through xn. This is now another expression for the probabilistic center of mass of y, the expectation of y. We have a very similar expression for the variance. Write s squared now again for the integral of the function value at a point, look at how far it is from M, square it, that is the squared deviation of the y value from the center M, weighted according to the probability mass density, integrate over all possibilities, and there you have it, the variance of y, and we'll write this more evocatively as a variance of f of x1 through xn. For the reader who is a little unsure about densities, she should go back and refer to Tableau 6 Part 2, where we flesh out these concepts in some more detail. With these under her belt, what she's got now is a way of characterizing in continuous spaces these ideas of a probabilistic center of mass and a probabilistic variance, the expectation and a variance.